Hello everyone. The title of my talk is Robust Optimization Using Machine Learning for Uncertainty Sets. My name is Teja Bandula, and this is joint work with Cynthia Rudin, also at MIT. Motivation. In decision making, sometimes we need to construct a policy before an unknown future scenario realizes. How then can we construct such a policy when we do not know the future? Can How can we ensure that with high probability the constructed policy will be robust to whatever the future brings? One possible approach is to construct an uncertainty set of possible future situations and use a robust or minimax optimization. Here, we can define the uncertainty set appropriately so that it captures most of the future scenarios so that our policy will be feasible for most of the time, or with high probability it will be feasible. Let's look at the example of portfolio allocation to further illustrate this. Here, I have listed the standard mathematical programming formulation for this problem. Here, we are trying to maximize a linear objective subject to three constraints. The linear objective is nothing but the portfolio return. The portfolio return is a linear combination of asset weights times the returns of the assets, and the asset weights are what we want to determine. We have constraints that the asset weights should sum up to 1. The variance of the portfolio should be upper bounded by a constant, and the portfolio weights should all be non-negative. Let's look at the robust optimization version. If the expected future returns are unknown, we will have to modify our previous optimization problem to a problem such as this, where we have the same set of constraints, but our objective has changed. Our objective is now a minimization of returns in the set U of R transpose pi. That is our new objective. What we are doing here is that we are trying to minimize our worst case future returns. So our overall optimization problem, which is the maximization of portfolio weights, gives us the best weights for the worst case realization of expected future returns. Now the question arises, how to construct or design the set U? As of course, if the set U is really big, then the policy pi will not be of high quality. There are multiple ways to construct set U. The first way is when you only have to rely on domain knowledge. In this case, you'll use your domain knowledge and other information, a priori information, to construct the set U as, for example, a product space of intervals. The second approach is if you had empirical statistics, that is, you had historical data of returns, let's say n day returns. Then what we can do is for each asset j, we can compute a fifth quantile and a 95th quantile and compute an interval, and we can define our uncertainty set U to be a product of all these intervals. That is, in the future, the expected future returns, we expect them to fall in this product space. If we have not just the historical returns but also the factors which can predict these returns, then we can do something slightly different. We can use some kind of statistical modeling or a prediction step instead. So that is this kind of approach has been done before in the context of linear regression, where we had to make strong distributional assumptions. In this work, we'll generalize that particular setting to the general setting of supervised learning and somehow transform our historical data into an uncertainty set that we can use in our optimization problem. So the goal is that we want to address the robust decision making setting when feature-rich data is available, and we want to go beyond linear regression. And what we will show is that we can leverage learning theory to design the required uncertainty set. We can also leverage learning theory to provide a probabilistic guarantee on the robust solution pi, which we will obtain as a result. So we'll look at proposed solution now. And in order to do so, I'll first show you the workflow for solving a deterministic problem. That is when we only construct a single model. What we'll do here is that once we have historical data, let's say features which can somehow predict the labels, then we'll use the historical data to construct our model beta. Then we'll use the model beta and evaluate and come up with predictions for our future feature vectors x tilde j is from 1 to m, to make m predictions. And those m predictions can potentially parameterize our optimization problem, and that will give us our solution pi. So the deterministic part is that the optimization problem has parameters which are not uncertain anymore, because we came up with m numbers that we inserted into our optimization problem. But that is generally not the case. So the actual workflow is going to be as follows, which is what is our proposed solution. It's going to involve a robust or minimax problem at the policy step. So what we'll do is we'll first take our historical data and pass it through a modeling step and obtain an uncertainty set U of possible future of possible labels that these features x tilde j from 1 to m can have. So hopefully the uncertainty set U can capture the labels with high probability. Then we'll just use the set U and formulate a minimax optimization problem in the policy step to compute a robust policy pi. So of course the U should capture the true labels of the future feature vectors x tilde j from 1 to m. But what we'll do here is that we'll show that U can be designed in a very principled manner, and we can also get a learning theory. We can also use learning theory to provide a probabilistic guarantee on the robust solution pi. So the policy step is as follows. If the deterministic decision problem is written as below, where we are trying to minimize our decision variable pi over a certain objective, and constraints written as f of pi comma u belonging to the cone k, then the robust optimization problem will be the minimization of a decision variable pi over over a slightly different objective, subject to the constraints holding for all values of u in our uncertainty set capital U. In the modeling step, which is what is gonna determine our uncertainty set U, we're gonna try to model two sources of uncertainty. The first source of uncertainty is the model effect. That is, the model built from finite data may not be the best-in-class model. In fact, there could be multiple good models. The second effect that will add to uncertainty is that the true labels may be different from model predictions, even if we know the best-in-class model. So we have to also account for that, so that our uncertainty set U can actually contain the true labels for these feature vectors x tilde jj from 1 to m with high probability. So since that is the case, we can decompose our uncertainty set U as a result of two effects, the model effect and the residual effect. What we're going to do is we're going to define two sets, U subscript b and U subscript minus b, and make our uncertainty set U be a cross product of these two sets. And each of these sets is actually captures precisely one of the effects. So U subscript b will capture the model effect, and U subscript minus b will capture the residual effect. Of course, while defining these sets, we also need the future feature vectors x tilde jj from 1 to m. The subscript b denotes that we are not sure which model that we are supposed to pick. We are supposed to pick the best-in-class model, but hopefully b represents a set of good models which also contains the best-in-class model potentially. So let's first look at the residual effect. For that, I need some notation. Let beta be the model in the model class b0. Let L be the loss function. Let LP be the expected loss of model beta. Let beta star be the best-in-class model, which we can obtain by minimizing the expected loss of models over the model class b0. Then we can use this best-in-class model b star to state one assumption, and the assumption is as follows. We know a pair which is a set E and a number delta E such that the differences between the labels and the predictions using the best-in-class model beta star is in the set E with high probability. That is, we know the set E which contains the model residuals using the best-in-class model beta star with high probability. If we know this, then we can straightforwardly define the set U subscript minus V, which is supposed to capture the residual effect, as simply the m times cross product of the set E. Now let's look at the model effect. For that, we need to know the notion of the normalized empirical error. Let LS denote the normalized empirical error. Let beta L be the model which minimizes the normalized empirical error. Let B be the set of good prediction models created from our data. Then what we do is we propose that the set of good models should have this particular form. That is, it's all models in our model class B naught such that their normalized empirical error is not too far off from the smallest normalized empirical error that we can achieve. We have a buffer term here, which is captured by the term C. So once we have defined our set of good models in this way, then we can define the set U subscript B in the following manner. It's the evaluation of all models in our set of good models on the set of future feature vectors x tilde 1 to x tilde m. So these are all the predictions using the set of good models. Once we have the definition of both U subscript B and U subscript minus B, we can now go forward and define the uncertainty set U as the cross product between these two sets, where we have already defined U subscript B and U subscript minus B as before. So this completely characterizes how we are going to define the uncertainty set using our training data, and then we can proceed to the policy step and solve to get a robust solution pi. So the workflow for which basically combines the modeling and policy steps is as follows. In the modeling step, we construct U subscript B and U subscript minus B. We define the set of good models using the historical data, which gives us U subscript B. We define U subscript minus B using a priori known set E as the m times cross product of the set E. Once we have defined an uncertainty set U, we can go forward and go to the policy step where we obtain a robust solution. And here we have a couple of options. If U subscript B and U subscript minus B are nice, then we can bound them using tractable sets, which are, for example, ellipsoids or boxes, as is typically done in robust optimization, and solve for the robust solution pi tractably. If that is not the case, then we can solve a sampled version of the decision making problem to get the robust solution pi, and it's a trade-off there. So let's go back and look at our proposed solution. So this was our workflow going from the historical data to an uncertainty set U to the robust solution pi. What we want to show now is that the way we have defined the uncertainty set U, and in particular the set of good models B, is actually sound, and in fact it leads us to a nice probabilistic guarantee on the robust solution pi. So let's focus on how we constructed the set of good models B in some detail. So we had proposed the form B as a set of all models such that their empirical error, normalized empirical error, is as low as possible to the lowest empirical error. We'll now expand the term C here, and for that we need to define empirical Rademacher average. It's just a property of the model class. For any arbitrary model class, it is H, it is defined in a certain way, given an arbitrary model class and our sample, which is the training data. So let's look at how we'll define the set of good models precisely. We can expand the buffer term C here in this way. So our set of good models becomes all the models in our model class B naught such that the normalized empirical error is upper bounded by the lowest normalized empirical error plus 2 times the Rademacher complexity of a certain function class plus an additive term which involves some constants. So this is the full characterization of the set of good models. For instance, when the loss function L is actually equal to just the square loss, we can just substitute the square loss representation here. And we can also have an upper bound on the empirical Rademacher average to get a full description of our set of good models, and we can then define u subscript b, u subscript minus b, and therefore the uncertainty set u, and then proceed along in our workflow. So let's see why this particular precise definition of the set of good models helps us in any way. And here is a theorem which supports that. What it says is that with probability 1 minus delta, the best-in-class model beta star belongs to the set of good models that we specified in the previous slide. So the set of good models B was specified in such a manner such that beta star belongs to the set with high probability. Now, the robust optimal solution pi star is feasible for the unknown feature vector labeled pairs, which are 1 to m, with probability at least 1 minus delta plus m delta e. That is, with high probability, our robust optimal solution is feasible for the true labels of the future feature vectors. Thus, we provide a guarantee that pi star will be robust to the unknown true label realizations. Thus, we have shown why the set of good models was defined in a certain way and how it allowed us to provide a probabilistic guarantee over the robust solution pi. So let's look at a couple of extensions. How do we define the set of good models for finite hypothesis classes? When B0 is finite, we can use the size of B0 rather than the Rademacher complexity to get the same robustness guarantees. So all that changes is that instead of 2 times the Rademacher complexity of a certain function class, we'll have this term here in the definition of the set of good models. The second extension is that we can also define the set of good models using pack-based theory. So let us have a prior distribution over the set of over our model class. Then we can pick all those models to be in our set of good models which satisfy a certain inequality. The inequality is that the normalized empirical error of the model should be upper bounded by the log of the probability probability value of that model minus some constant divided by some other constants. What this says is that if the prior on a certain model is high, then we can allow for a higher value of normalized empirical error and still include that model in our set of good models. If the prior on a certain model is low, then we better have that the normalized empirical error of that model be low for it to be also low for it to be in our set of good models. In this case, the robustness guarantee stated earlier is not applicable, but this is still a principled way to use the historical data and our prior knowledge and combine them to define a set of good models. So let's compare the proposed solution with linear regression as a final step. So in linear regression, the only thing that changes is that we are assuming something at the modeling step, and as a result of which the way we define our uncertainty set can also change. And what is that change is what I'll detail next. In particular, in the modeling step, this is what we assume. We assume that the labels are precisely equal to a transformation of the features plus an additive noise, and the additive noise is normal with a certain variance. In fact, when we have linear models, then we have a closed form expression for the estimated model. Using the estimated model, we can actually get a a confidence interval type bound on how far the estimated model is away from the true model. And in doing so, we can use the chi-square distribution or F distribution uh, based analysis to come up with a set of good models. So the set of good models is all models such that this right hand side value is upper bounded by a certain chi-square distribution quantile value C. So this is actually a quadratic actually an ellipsoid constraint for ellipsoid constraint, and so our set of good models looks like an ellipsoid geometrically. So using this set of good models, we can now again compute our uncertainty set, the part of the uncertainty set, which is u subscript b appropriately. We can also define u subscript minus b using the normal distribution assumption that we had for the additive noise. And when we combine these two, we get the usual uncertainty set, and then we can proceed again with robust optimization formulation in the policy step to compute a policy. Of course, this involves making certain assumptions on the structural form of the relation between the features and the labels, which was not necessary for our general supervised learning setting. And also, here the set description is making use of certain distributional properties because of the distribution we assumed of the noise. We are not making any distributional assumptions in our general setting. So in summary, we show a new way to do robust optimization in the context of feature-rich data. We propose a principal way to design uncertainty sets using learning theory tools, both uniform convergence and path-based theory-based. We showed a probabilistic guarantee on the robust optimal solution, and we contrasted the proposed solution with the setting of linear regression. Thank you.